You exist. The chair beneath you exists. The planet spinning through space exists. 13.8 billion years of cosmic history exist. But why does any of it exist at all? Why is there something rather than nothing? This question has tormented philosophers for millennia and driven scientists to the edge of comprehension. Tonight, we journey to the precipice where physics meets metaphysics, where equations dance with infinity, and where the very concept of nothingness dissolves into quantum uncertainty. We stand at humanity's greatest frontier, attempting to understand how everything emerged from the void. Close your eyes for a moment and try to imagine true nothingness. Not darkness, because darkness is something. Not empty space, because space is something. Not silence, because silence requires time in which no sound occurs, and time is something. Try to imagine the complete absence of everything. No matter, no energy, no space, no time, no physical laws, no mathematics, no potential for anything to ever exist. This is what philosophers call absolute nothingness, and it is quite possibly the most difficult concept for the human mind to grasp. Our brains evolved to navigate a world of objects and forces, causes and effects, past and future. We are pattern recognition machines optimized for survival in a universe that already exists. Asking us to conceive of non-existence is like asking a fish to imagine a world without water. The very act of imagination requires a mind, which requires a brain, which requires atoms, which requires a universe. We cannot step outside existence to view it from the perspective of nothingness, because there is no perspective in nothingness. There is no outside. There is no view. The question itself seems almost absurd when you truly contemplate it. Look around you. Reality is not subtle. Stars explode across billions of light years. Galaxies collide in slow-motion cosmic catastrophes. Black holes devour space-time itself. The universe screams its existence from every direction. Yet beneath this overwhelming presence lurks an absence that defies understanding. Before there was something, there was nothing. Or was there? That simple word, nothing, may be the most deceptive concept in all of human language. Ancient civilizations wrestled with this mystery through mythology. The Babylonians imagined primordial chaos giving birth to order. In their creation epic, the Enuma Elish, the universe began when the freshwater god Apsu and the saltwater goddess Tiamat mingled their waters. From this mixing came the younger gods, and from their conflict came the ordered cosmos. The Egyptians envisioned a cosmic egg emerging from infinite waters called Nu, the primordial ocean that contained all potential. When the egg hatched, the sun god Ra emerged and began the work of creation, separating sky from earth, light from darkness, order from chaos. Hindu cosmology described endless cycles of creation and dissolution, spanning incomprehensible timescales. The universe breathes in and out over periods called kalpas, each lasting billions of years. Brahma dreams the universe into existence, and when he awakens, it dissolves back into potential. These weren't merely stories told around campfires to entertain children. They were humanity's first serious attempts to grapple with an existential crisis embedded in consciousness itself. How can being emerge from non-being? The question feels almost paradoxical, like asking what happens when an irresistible force meets an immovable object. If nothing exists, how can anything begin? If something exists, how did it overcome the barrier of nothingness to arrive at existence? The ancient Greek philosophers approached the problem with pure reason, attempting to solve it through logic rather than mythology. Parmenides of Elea, living in the 5th century before the Common Era, made a radical claim that would echo through philosophy for millennia. He declared that nothing cannot exist because even the concept of nothing is something. To speak of nothing, to think of nothing, to reference nothing, is already to make nothing into something. Therefore, he argued, the universe must be eternal and unchanging, with all apparent change being mere illusion. Reality is one, continuous, and everlasting. The multiplicity and motion we observe are tricks of the senses, distortions in our perception that obscure the unchanging unity of being. His student Melissus extended this logic with rigorous precision. If the universe had a beginning, he reasoned, it must have come from nothing, which is impossible. Nothing cannot produce something. Therefore the universe is without beginning or end. It stretches infinitely in time and space, eternal and immutable. This argument had a certain austere elegance, but it clashed violently with ordinary experience. We see things begin and end constantly. Stars are born and die. Civilizations rise and fall. Even mountains erode over time. How could all of this be illusion? Aristotle, the most influential philosopher of antiquity, attempted a middle path. He agreed that the universe must be eternal, arguing that time itself requires change, and change requires things that change, so there could never have been a time when nothing existed because that would be a time without time, a contradiction. But unlike Parmenides, Aristotle allowed for constant change within the eternal cosmos. The universe is a great machine in perpetual motion, with the unmoved mover, a necessary being that exists beyond the physical universe, serving as the ultimate source of all motion without itself moving or changing. The idea of creation from nothing seemed to violate the most basic principle of logic that would later be formalized as the principle of sufficient reason. For everything that exists, there must be a reason why it exists rather than not existing. For every event that occurs, there must be a cause that brought it about. From nothing, nothing comes. This principle seemed self-evident, as obvious as mathematical truths, yet it created an inescapable dilemma. Either the universe is eternal, which seemed to push explanation back infinitely without ever reaching a foundation, or the universe had a beginning, which required explaining how something came from nothing. Medieval Islamic and Christian philosophers grappled with this dilemma in the context of religious cosmology. They needed to reconcile philosophical reasoning with scriptural accounts of creation. Al-Ghazali argued that God created the universe from nothing through an act of will that transcended causation. Time itself was created along with the universe, so there was no before creation for God to exist in. God exists outside of time, in eternity, which is not everlasting time but a different mode of being altogether. This solution preserved both creation and causation by placing the creator outside the causal chain. Thomas Aquinas approached the problem differently. He argued that while reason could not definitively prove the universe had a beginning, revelation confirmed it. He distinguished between two types of causation: efficient causes operating in time and the sustaining cause of God holding the universe in existence at every moment. Even if the universe were eternal in time, it would still require God as its sustaining cause. Without God's continuous creative act, the universe would collapse into nothingness. In this view, creation is not just an event in the past, but an ongoing process happening at every instant. But these theological solutions push the question back rather than answering it. Why does God exist rather than nothing? If God is necessary, why is necessary existence possible? What determines which things exist necessarily and which contingently? The mystery of being versus non-being remained, now relocated to the divine realm rather than the physical cosmos. Enlightenment thinkers returned to purely natural explanations. Baruch Spinoza identified God with nature itself, arguing that the universe is a necessary being that could not fail to exist. Its existence requires no external cause because its essence includes existence. Gottfried Leibniz developed the principle of sufficient reason into a complete metaphysical system, arguing that this is the best of all possible worlds, because God, being perfectly rational, would choose the optimal universe from all possibilities. But this raised the question of why anything is possible at all, why there is a space of possible worlds rather than no space of possibilities. Immanuel Kant argued that reason reaches its limits when confronting questions about the universe as a whole. We cannot prove the universe had a beginning or that it is eternal. Both positions lead to contradictions when pushed to their limits. This is one of his famous antinomies of pure reason, demonstrating that human cognition is not equipped to answer certain metaphysical questions. We can know the phenomena, the world as it appears to us, but not the noumena, the world as it is in itself. The ultimate origin of reality lies beyond the reach of pure reason. Yet by the 20th century, physics had discovered something profoundly disturbing that cut through millennia of philosophical debate. The universe is not eternal. It had a beginning. In 1929, Edwin Hubble's observations at the Mount Wilson Observatory revealed that distant galaxies are racing away from us in all directions. The universe is expanding. This was not merely an academic discovery published in obscure journals. It fundamentally transformed humanity's understanding of cosmic history. Run the clock backward and everything converges to a point. a singularity, a moment of creation approximately 13.8 billion years ago that we call the Big Bang. This discovery transformed the question of cosmic origins from philosophical speculation into scientific investigation. Suddenly, we had observational evidence constraining our theories. The universe was born. It had a beginning in time. The ancient Greek assumption of eternity was shattered by astronomical observation. But this discovery also made the problem more acute, more pressing, more urgent. If the universe had a beginning, what came before? And how can something begin from nothing without violating every principle of physics we hold dear? The question philosophers had debated for millennia was now a scientific problem demanding answers from cosmology, quantum mechanics, and the still mysterious theory of quantum gravity that physicists were struggling to formulate. The Big Bang is perhaps the most misunderstood concept in all of science. Popular imagination pictures it as an explosion in space, like a cosmic firecracker detonating in a pre-existing void. This mental image is completely wrong. The Big Bang was not an explosion in space. It was an explosion of space itself. Space and time came into existence together at that moment. There was no void waiting to be filled because the concept of space did not exist. There was no ticking clock counting down to zero because time itself began at the Big Bang. This misconception runs deep in our collective understanding. Movies and television shows depict the Big Bang as a bright explosion expanding into darkness, stars flying outward like shrapnel. Science communicators struggle against this imagery because our brains are wired to think of events happening in space and time. We cannot help but imagine a before and an after, a here and a there. But the Big Bang defies these categories. It was not an event that happened somewhere. It happened everywhere simultaneously because everywhere was compressed to a point. The evidence for the Big Bang accumulated throughout the 20th century, each observation adding another piece to the puzzle. Edwin Hubble's 1929 discovery that galaxies are receding from us was the first hint. By measuring the redshift of distant galaxies, Hubble showed that the universe is expanding. The farther away a galaxy, the faster it recedes. This relationship, now called Hubble's law, implies that in the past everything was closer together. Extrapolate backward and you reach a moment when all matter occupied the same point. But observation of expansion alone did not prove the Big Bang. It suggested a dynamic universe rather than a static one, but other explanations were possible. The steady-state theory, championed by Fred Hoyle, proposed that the universe has always been expanding, but new matter continuously appears to maintain constant density. The universe would be eternal, with no beginning, avoiding the conceptual difficulties of creation from nothing. The decisive evidence came in 1965 when Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation. They were testing a sensitive radio antenna at Bell Labs when they detected a persistent hiss of radio noise coming from all directions in the sky. Initially, they thought their antenna was contaminated, possibly by bird droppings. They cleaned it meticulously. The noise remained. Eventually, they realized they had discovered the afterglow of creation itself. The cosmic microwave background is radiation left over from when the universe was about 380,000 years old. Before this time, the cosmos was so hot that atoms could not form. Electrons and nuclei existed as a plasma, opaque to light. Photons scattered constantly off free electrons, unable to travel far. Then the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Light decoupled from matter and began travelling freely through space. That ancient light, stretched to microwave wavelengths by cosmic expansion, is what Penzias and Wilson detected. The temperature of this radiation, about 2.7 degrees above absolute zero, precisely matches predictions from Big Bang cosmology. Its spectrum is a perfect black body, exactly what thermal radiation from the early universe should look like. The cosmic microwave background provides a baby picture of the cosmos, showing the universe as it was in its infancy. This discovery demolished the steady-state theory and established the Big Bang as the standard model of cosmology. But the cosmic microwave background tells us far more than just that the Big Bang happened. Its tiny temperature fluctuations, varying by only about 1 part in 100,000 across the sky, encode information about the early universe with extraordinary precision. These fluctuations represent quantum fluctuations from the first instance of existence, inflated to cosmic scales and imprinted on the radiation field. They are the seeds from which all structure in the universe grew. In the 1990s, the Cosmic Background Explorer satellite mapped these fluctuations for the first time, revealing a mottled pattern across the sky. Slightly hotter regions appeared in red, slightly cooler in blue. The variations were minute, but they were real and measurable. This discovery earned John Mather and George Smoot the Nobel Prize in Physics in 2006. The pattern was not random. It showed specific statistical properties predicted by inflationary cosmology. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured these fluctuations with unprecedented precision. The data revealed acoustic peaks in the power spectrum, showing how sound waves propagated through the primordial plasma before atoms formed. These waves compressed and rarefied the plasma, creating regions of higher and lower density that would eventually become galaxy clusters and cosmic voids. The spacing of the peaks depended on the geometry of the universe, the density of matter and energy, and the conditions in the very early cosmos. The Planck satellite, operating from 2009 to 2013, pushed measurements to even greater precision. It confirmed that the universe is spatially flat to within a fraction of a percent. It measured the cosmic density of normal matter, dark matter, and dark energy. It constrained the parameters of inflationary models. Every measurement agreed with the theoretical framework cosmologists had developed, providing stunning confirmation that we understand cosmic history from microseconds after the Big Bang to the present day. But the cosmic microwave background also revealed something puzzling. The temperature should be the same in all directions because different regions of the sky appear to have been in thermal equilibrium, at the same temperature in the early universe. Yet according to standard Big Bang theory without inflation, these regions were never in causal contact. Light had not had time to travel between them since the beginning. How could they have the same temperature if they never communicated? This is the horizon problem, one of the key puzzles that inflation was invented to solve. In standard Big Bang cosmology, the universe expanded relatively slowly in its early moments. The distance light could travel, the causal horizon, was smaller than the observable universe. Regions on opposite sides of the sky are separated by distances larger than light could have crossed. They should have different random temperatures, yet they are identical to 1 part in 100,000. Inflation solves this by proposing that the universe underwent exponential expansion in its first fraction of a second. Before inflation, the entire observable universe was compressed into a region tiny enough for light to cross it many times, establishing thermal equilibrium. Then inflation stretched this small equilibrated region to cosmic scales. Regions now separated by billions of light years were once in contact, which explains their uniform temperature. This creates an immediate, logical problem. We're accustomed to thinking of causes preceding effects in time. The cue ball strikes the 8-ball moves, cause, then effect. But at the Big Bang, time itself began. There was no before the Big Bang for a cause to exist in. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question uses familiar words, but the words have no meaning in this context. Direction doesn't extend beyond the poles. Time doesn't extend before the Big Bang. Or does it? Here we encounter the first great mystery. Maybe the question is meaningless. Maybe time simply began, and asking about before is nonsensical. This is one possibility. But another possibility lurks in the shadows of physics. Perhaps there was something before the Big Bang, but it was so alien, so unlike anything in our experience, that ordinary concepts like time and causation break down. Perhaps the beginning of our universe was not the beginning of everything. When we trace the cosmic expansion backward, the entire observable universe, everything we can see in any direction, compresses into a region smaller than an atom. The density becomes infinite. The temperature becomes infinite. The curvature of space-time becomes infinite. Mathematics throws up its hands in despair. Physicists call this a singularity, which is a polite way of saying our equations stop working. The singularity is not a physical place. It's a mathematical confession of ignorance. Understanding what a singularity truly represents requires delving into the nature of mathematical models. In physics, we describe reality using equations. These equations work magnificently within certain ranges. Newton's laws predict planetary motion with exquisite accuracy. Maxwell's equations explain electricity and magnetism. Einstein's field equations describe the bending of spacetime around massive objects. But every equation has limits beyond which it fails. A singularity marks such a limit. It is a point where the equations yield infinity as an answer, which physically means the model has broken down. Infinities are red flags in physics. They signal that we are asking questions the theory cannot answer. The singularity at the Big Bang tells us that general relativity, which works beautifully to describe the evolution of the universe from microseconds after creation to the present day, cannot describe the moment of creation itself. This limitation is not unique to cosmology. General relativity also predicts singularities at the centers of black holes. If you fall past the event horizon and continue toward the center, the equations say you encounter infinite density and infinite spacetime curvature. Does this infinity really exist? Almost certainly not. More likely, quantum effects become important at small scales and prevent the formation of a true singularity. But we lack a theory of quantum gravity to describe what actually happens. The Big Bang singularity poses a similar challenge but on a grander scale. At the earliest moments when the universe was incredibly small and dense, quantum mechanics must have been crucial. Every particle in the universe existed in a region smaller than an atom. Under these conditions, the probabilistic, uncertain nature of quantum reality would dominate. You cannot describe the universe using only general relativity, which is a classical theory that assumes space-time is smooth and well-defined. You need quantum gravity. Roger Penrose and Stephen Hawking proved singularity theorems in the 1960s, showing that under very general conditions, Einstein's equations predict singularities are inevitable in gravitational collapse and in cosmology. These theorems demonstrated that the singularity is not an artifact of assuming perfect symmetry. Even a lumpy, asymmetric universe headed toward gravitational collapse will form a singularity. The theorems assume that general relativity is valid all the way down, but this assumption must fail at some point. General relativity, Einstein's masterwork that describes gravity as the curvature of spacetime, breaks down at the singularity. The theory predicts its own demise. As we approach the moment of creation, quantum effects become impossible to ignore. Gravity itself becomes quantum mechanical. But we don't have a complete theory of quantum gravity. General relativity describes gravity on large scales. Quantum mechanics describes the behavior of subatomic particles. They are both spectacularly successful in their domains, but they speak different mathematical languages and refuse to merge into a single coherent picture. This is not merely a technical problem. It represents a fundamental gap in our understanding of reality. At the scale of the Planck length, about 10 to the power of negative 35 meters, and the Planck time, about 10 to the power of negative 43 seconds, space-time itself becomes grainy and uncertain. Below these scales, the very concepts of distance and duration lose meaning. The smooth fabric of space-time Einstein described tears apart into quantum foam. Wormholes flash in and out of existence. Virtual black holes appear and disappear. Causality becomes probabilistic. The singularity at the Big Bang represents the instant where quantum mechanics and gravity meet head-on in a cosmic collision. Neither theory alone can describe what happened. We need quantum gravity, and despite decades of effort from thousands of the brightest minds in physics, we still don't have it. String theory, loop quantum gravity, and other approaches have made progress, but the complete picture remains frustratingly out of reach. This means that when we ask how the universe began, we're asking a question that requires physics we don't yet possess. Yet we can still make progress by approaching the boundary of our knowledge carefully. We may not understand the singularity itself, but we can understand what happened immediately after. By running the clock backward to the Planck time, we reach the edge of what current physics can describe. Beyond that edge lies terra incognita. But right at that edge, something extraordinary happens. The universe becomes so small and so energetic that quantum mechanics takes over completely. And quantum mechanics, unlike classical physics, allows for possibilities that seem impossible in everyday experience. Imagine the universe at one Planck time after the Big Bang. This instant occurred at approximately 10 to the power of negative 43 seconds after the moment of creation. To put this timescale in perspective, there are more Planck times in 1 second than there have been seconds in the entire age of the universe. It is the smallest meaningful unit of time, the quantum of temporality itself. Below this threshold, time loses definition in the same way that trying to measure the position of an electron to infinite precision becomes meaningless in quantum mechanics. The Planck time derives from fundamental constants of nature. Take the speed of light, which governs the structure of space-time. Take Planck's constant, which sets the scale of quantum effects. Take Newton's gravitational constant, which determines the strength of gravity. Combine these three in the right way, and you get a time, approximately 5.39 times 10 to the power of negative 44 seconds. This is not arbitrary. It emerges from the fundamental fabric of reality. Similarly, the Planck length, about 1.6 times 10 to the power of negative 35 meters, represents the smallest meaningful distance. Below this scale, quantum fluctuations of spacetime become so violent that the concept of distance breaks down. You cannot measure a length smaller than the Planck length, because the measurement would require concentrating so much energy in such a small region that you would create a black hole. The very act of measurement destroys what you're trying to measure. At the Planck epoch, the entire observable universe, which today spans 93 billion light-years, occupied a volume smaller than the Planck length cubed. Everything we can see, from the most distant quasars to the atoms in your body, was compressed into a region so small it defies visualization. This was not empty space with matter squeezed into it. Space itself was that small. The geometry of the universe was wrapped up tighter than the quantum uncertainty principle can resolve. At this moment, the entire observable universe occupied a volume smaller than an atomic nucleus. Not just the matter in the universe, but space itself. The temperature exceeded 10 to the power of 32 Kelvin, a number so large that it defies intuition. Every elementary particle we know about today existed only as pure energy. Matter had not yet condensed from the primordial fire. The four fundamental forces that govern reality today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. The universe was symmetric in a way it has never been since. This unification represents one of the deepest insights in modern physics. At low energies, the four forces appear completely different. Gravity is always attractive and acts over infinite range, but is incredibly weak. It takes the entire mass of Earth to hold you to the ground. Electromagnetism can be attractive or repulsive, acts over infinite range, and is vastly stronger than gravity. The strong nuclear force holds quarks together inside protons and neutrons with even greater strength, but only over distances smaller than an atomic nucleus. The weak force drives radioactive decay and operates at even shorter ranges. These differences seem fundamental, but they are illusions created by symmetry breaking. As temperatures increase, the distinctions blur. The Weinberg-Salem theory, confirmed experimentally in the 1970s, shows that electromagnetism and the weak force merge into a single electro-weak force at energies around 100 GeV, achievable in particle accelerators. Grand unified theories propose that at around 10 to the power of 16 GeV, the strong force joins them, and at the Planck energy, approximately 10 to the power of 19 GeV, gravity itself enters the unified picture. This energy scale is staggering. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies around 10 to the power of 4 GeV. The Planck energy exceeds this by 15 orders of magnitude. We will never build an accelerator powerful enough to test physics at the Planck scale directly. Our knowledge of this epoch comes entirely from theoretical extrapolation, guided by symmetry principles and mathematical consistency. In the Planck epoch, particles as we know them did not exist. The distinction between matter and energy was meaningless. Everything was energy in various quantum states. The quarks, electrons, photons, and neutrinos that populate the universe today were indistinguishable from each other. They were different oscillations of a unified quantum field, related by the perfect symmetry of the superforce. This symmetry is profound. In everyday experience, these forces are wildly different. Gravity holds planets in orbit. Electromagnetism powers lightning and holds atoms together. The strong force binds quarks into protons. The weak force drives radioactive decay. They operate at different strengths, over different ranges, through different mechanisms. Yet in the Planck epoch, they were one. This unification is not mere speculation. As we accelerate particles to higher energies in colliders, we see hints of this unity. The electromagnetic force and weak force merge into the electro-weak force at energies achievable in laboratories. Grand unified theories predict that at still higher energies, the strong force joins them. And at the Planck energy, gravity itself enters the fold. The state of the universe during the Planck epoch can barely be called a state at all. Quantum fluctuations dominated completely. The very fabric of space-time writhed and bubbled like boiling water. Tiny wormholes connecting different regions of space appeared and vanished. Virtual particles materialized from the vacuum and annihilated back into it. The smooth geometry Einstein described gave way to what physicist John Wheeler called quantum foam, a roiling sea of probabilistic space-time. Wheeler coined this term in the 1950s, trying to capture the essential strangeness of quantum gravity. Imagine zooming in on space-time with increasingly powerful magnification. At everyday scales, space-time looks smooth, like a calm ocean viewed from an airplane. Zoom in closer and you might see small ripples, analogous to gravitational waves. Zoom in further, down to atomic scales, and quantum mechanics becomes important, but space-time itself still looks smooth. But continue down to the Planck scale, and the picture transforms completely. Space-time becomes a frothing foam of quantum fluctuations. Wormholes open and close. Virtual black holes appear and disappear. The smooth continuum dissolves into discrete quantum geometry. These were not small corrections to classical physics. They were the dominant reality. Heisenberg's uncertainty principle, which normally affects only subatomic particles, governed the universe itself. You cannot simultaneously know the exact position and exact momentum of a particle. At cosmic scales in the Planck epoch, you could not simultaneously know the exact geometry of space and its rate of change. Space-time itself became uncertain, smeared out across a range of possible configurations. This uncertainty is not ignorance, it is fundamental to reality. Before a measurement, a quantum particle exists in a superposition of all possible states simultaneously. The electron is here and there and everywhere at once until observation collapses the wave function. In the Planck epoch, the universe itself existed in superposition. Different geometries, different energy densities, different configurations of the primordial quantum fields all coexisted in quantum limbo. The universe was not a single definite thing, it was a probability cloud of all possible universes. Understanding what this means requires abandoning our classical intuitions completely. We are accustomed to a universe that has definite properties. The table is here, not there. The temperature is this value, not that one. But quantum mechanics tells us that at its deepest level, reality is not definite until measured. And in the Planck epoch, there was no external observer to collapse the wave function. The universe measured itself through its own internal quantum processes, a concept so strange that physicists still argue about what it means. The Planck epoch ended as the universe expanded and cooled. At around 10 to the power of -36 seconds, the temperature dropped low enough for the unified superforce to undergo its first phase transition. Gravity separated from the other forces. The universe lost its perfect symmetry and gained the asymmetry that defines our reality. This breaking of symmetry is itself a profound mystery. Why did symmetry break in this particular way and not another? The laws of physics we observe depend on how this symmetry breaking occurred. Different patterns of symmetry breaking would yield different physical laws, different particles, different forces. In some sense, the universe made a choice during this epoch, and that choice determined everything that followed. Yet the Planck epoch does not answer our fundamental question. It pushes it back one level. If the universe emerged from the Planck epoch in this highly excited, extremely hot, perfectly symmetric state, where did that state come from? What set the initial conditions? Here we reach the boundary between physics and metaphysics, between what we can calculate and what we can only speculate. But modern physics has discovered something remarkable. The quantum vacuum is not empty. Nothing, it turns out, is not nothing. This statement sounds contradictory, but it captures one of the deepest insights of quantum field theory. When we remove all particles from a region of space, evacuate all matter and energy, eliminate every last atom and photon, we might think we have created a true void. But quantum mechanics says otherwise. The vacuum seethes with activity. This discovery emerged gradually through the 20th century as physicists developed quantum field theory to describe fundamental particles. Paul Dirac's equation for the electron, formulated in 1928, predicted the existence of antimatter, but it also revealed something strange about the vacuum. The equation allowed for states with negative energy, which seemed unphysical. Dirac proposed that the vacuum is actually a sea of negative energy particles, completely filling all negative energy states. An electron in this sea is invisible because it is indistinguishable from the background. But if you give enough energy to one of these negative energy electrons, it jumps to a positive energy state, leaving behind a hole. This hole appears as a positron, the electron's antiparticle. This picture was refined as quantum field theory developed. We now understand the vacuum as the lowest energy state of quantum fields, but this lowest energy state is far from empty. Quantum fields must fluctuate even in their ground state because of the uncertainty principle. The electromagnetic field, the electron field, the quark fields, all of them experience zero-point fluctuations that never cease. Virtual particles constantly pop into existence in pairs and annihilate back into the void. An electron and positron appear from nothing, exist for a fleeting instant allowed by Heisenberg's uncertainty principle, then destroy each other before the universe's bookkeeping notices the violation of energy conservation. These are not mere mathematical artifacts, they are real in a profound sense. Virtual particles affect the energy levels of atoms, creating the Lamb shift that can be measured in laboratories. They generate a force between metal plates in the Casimir effect, physically pushing the plates together. The quantum vacuum is a bubbling sea of transient existence. The Casimir effect provides particularly direct evidence for vacuum fluctuations. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in vacuum would experience an attractive force. This seems impossible. The plates are uncharged and neutral. What could push them together? The answer is virtual photons. In the vacuum between the plates, only certain wavelengths of virtual photons can exist. The plates act like boundaries that limit which standing waves can form, similar to how a violin string can only vibrate at certain frequencies determined by its length. Outside the plates, all wavelengths of virtual photons fluctuate freely. This creates a pressure difference. More virtual photons push on the plates from outside than from inside. The pressure difference generates a measurable force. This prediction was confirmed experimentally, first crudely in 1958, and then with increasing precision in subsequent decades. The Casimir force has been measured down to the nanometer scale. It is not large, but it is real and measurable. Vacuum fluctuations have physical consequences. The vacuum is not empty. This activity traces its origin to the uncertainty principle. At the quantum scale, you cannot pin down both the energy of a system and the time interval over which you measure it with arbitrary precision. The product of these uncertainties must exceed Planck's constant divided by 4 pi. This means that over sufficiently short time intervals, energy conservation can be violated. Particles can borrow energy from the vacuum, briefly exist in defiance of classical physics, then return that energy before the cosmic ledger demands payment. The mathematical formulation of this principle comes from the non-commutivity of quantum operators. In quantum mechanics, measurements of incompatible observables cannot be performed simultaneously with arbitrary precision. Energy and time form such a complementary pair. The more precisely you know when something happens, the less precisely you know its energy. For very short time intervals, the energy uncertainty becomes enormous, allowing massive particles to briefly pop into existence. In everyday circumstances, these fluctuations average out to zero. Virtual particles appear and disappear so rapidly that their net effect is negligible on macroscopic objects. But near black holes, something extraordinary happens. If a virtual particle pair forms at the event horizon, and one particle falls into the black hole while the other escapes, the escaping particle becomes real. Energy is drained from the black hole to pay the debt to conservation laws. The black hole shrinks. This is Hawking radiation, predicted by Stephen Hawking in 1974. Black holes evaporate through quantum processes, converting their mass into radiation over timescales that dwarf the age of the universe. Hawking's calculation was revolutionary. It showed that black holes are not truly black. They emit radiation with a thermal spectrum characterized by a temperature inversely proportional to their mass. A solar mass black hole has a temperature of about 60 billionths of a Kelvin, far colder than the cosmic microwave background. Such a black hole actually absorbs more radiation than it emits and grows over time, but a microscopic black hole, if such things exist, would be much hotter and would evaporate rapidly. This discovery merged quantum mechanics, general relativity, and thermodynamics in a profound way. Black holes have entropy proportional to their surface area. They have temperature. They obey the laws of thermodynamics. The vacuum fluctuations at their event horizons are not just mathematical curiosities, but drivers of real physical processes that determine the ultimate fate of these gravitational behemoths. The quantum vacuum also possesses energy density. Quantum field theory predicts that even empty space has a baseline energy, sometimes called zero-point energy. Every quantum field contributes to this energy. The electromagnetic field fluctuates. The electron field fluctuates. Every field in nature adds its quantum jitters to the vacuum. Calculating this energy density yields a result that is perhaps the most embarrassing prediction in the history of physics. The calculated value exceeds the observed vacuum energy density by a factor of 10 to the power of 120. This is the cosmological constant problem, a discrepancy so enormous that it suggests we fundamentally misunderstand something about quantum field theory or gravity or both. Yet despite this theoretical catastrophe, one fact remains clear. The vacuum has energy. And energy, through Einstein's equation E equals mc squared, is equivalent to mass. The vacuum has weight. It curves space-time. And in the early universe, this vacuum energy may have played the starring role in creation itself. Consider the universe at the Planck epoch. Quantum fluctuations were not small perturbations. They were the dominant feature of reality. The energy density of the vacuum exceeded the energy density of matter by unimaginable factors. Different regions of this seething quantum foam had different energy densities, different field configurations, different quantum states. And according to quantum mechanics, all of these possibilities existed simultaneously in superposition. Now here is where things become truly strange. In classical physics, a system in a high-energy state will tend to decay to a lower energy state. A ball at the top of a hill rolls down, water flows downhill seeking the lowest level. This is the second law of thermodynamics driving systems toward equilibrium. But quantum mechanics allows for tunneling. A particle can pass through a barrier it does not have enough energy to climb over. It tunnels through the barrier, appearing on the other side as if by magic. This is not speculative. Alpha decay in radioactive nuclei proceeds through quantum tunneling. We use this effect in tunnel diodes and scanning tunneling microscopes. If a particle can tunnel through a barrier, could the universe itself tunnel from one quantum state to another? Could the entire cosmos be a quantum fluctuation that tunneled into existence? This question brings us to the frontier of cosmology, where quantum mechanics meets the origin of everything. In December of 1979, a young physicist named Alan Guth sat alone in a room at the Stanford Linear Accelerator Center, working late into the night on a problem that seemed completely unrelated to cosmology. He was trying to understand magnetic monopoles, hypothetical particles predicted by grand unified theories of particle physics, but never observed in nature. Why don't we see magnetic monopoles? The mathematics said they should be common. Reality said they were absent. Guth had spent years struggling to find permanent academic employment, moving from one postdoctoral position to another. His wife, Susan, had followed him from Princeton to Columbia, to Cornell to Stanford. At age 32, he was still uncertain about his future in physics. The monopole problem was a side project, something to work on while he searched for his next position. He had no idea he was about to revolutionize cosmology. The magnetic monopole problem traced back to Paul Dirac's work in the 1930s. Dirac showed that if even a single magnetic monopole exists anywhere in the universe, it would explain why electric charge comes in discrete units. The quantum of electric charge is related to the magnetic charge of the monopole through a simple equation. This was an elegant result, but no monopoles had ever been found despite extensive searches. Grand unified theories made the problem acute. These theories predicted that monopoles should be copiously produced in the early universe during phase transitions as temperatures cooled. The calculation suggested the universe should be completely dominated by monopoles, with their mass density far exceeding that of ordinary matter. Yet we observe none. This was not just an absence of evidence, it was evidence that something was wrong, either with grand unified theories or with our understanding of the early universe. Guth was exploring an idea. What if the early universe underwent a phase transition, like water freezing into ice, and this transition somehow suppressed monopole production? as he worked through the mathematics, he realized something extraordinary. The phase transition would release enormous amounts of vacuum energy. This energy would act like anti-gravity, causing space to expand exponentially fast. And this expansion would dilute any monopoles produced in the earlier universe to near non-existence, explaining why we don't see them today. But as Guth stared at his equations, he realized this exponential expansion solved far bigger problems than magnetic monopoles. It solved the flatness problem. The universe's geometry is remarkably flat, neither curved like a sphere nor curved like a saddle. This flatness requires the cosmic density to be extraordinarily close to a critical value, 1 part in 10 to the power of 60 at the Planck time. Any deviation from this value would be amplified by cosmic expansion, making the universe either recollapse immediately or expand so fast that galaxies could never form. Why is the density tuned so precisely? Guth's exponential expansion stretched a tiny region of space to cosmic scales, flattening out any initial curvature like inflating a balloon smooths out wrinkles on its surface. The flatness problem had bothered cosmologists for years. Robert Dicke had emphasized it in lectures Guth attended at Cornell. The universe resembles a pencil balanced on its point. Any tiny deviation from perfect balance causes it to fall, yet the universe maintains this balance for billions of years. In standard Big Bang cosmology, this required incredibly precise initial conditions that seemed absurdly fine-tuned. No one could explain why the universe would start in such a special state. It solved the horizon problem. The cosmic microwave background radiation, the faint glow of the Big Bang visible in every direction, has almost exactly the same temperature everywhere. Variations are less than 1 part in 100,000. Yet according to standard Big Bang theory, regions on opposite sides of the sky have never been in causal contact. Light has not had time to travel between them since the beginning. How can regions that have never communicated have the same temperature? It's like finding 2 people on opposite sides of Earth speaking the exact same obscure dialect despite never having contact with each other's ancestors. Guth's exponential expansion solved this by making the observable universe expand from a tiny region that was in thermal equilibrium. Everything we see today came from a region small enough to have the same temperature. The horizon problem was equally puzzling. The observable universe today is about 93 billion light-years across. Light has only had 13.8 billion years to travel since the Big Bang. By rights, regions separated by more than about 13.8 billion light-years should never have been in causal contact. Yet the temperature is the same everywhere to exquisite precision. How did distant regions coordinate to have the same temperature without ever communicating? Standard cosmology had no answer. You could postulate that the initial conditions just happened to be incredibly uniform, but this felt like cheating. It was inserting by hand what the theory should explain. Inflation solved it naturally. Before inflation, the entire observable universe was much smaller than the horizon. All parts were in causal contact and could reach thermal equilibrium. Then inflation stretched this small region to cosmic scales, carrying regions far beyond each other's horizons while preserving their identical temperatures. Guth scribbled in his notebook, "Spectacular realization. This mechanism solves the flatness and horizon problems." The words barely captured the magnitude of what he had discovered. In a single insight, he had explained 3 of cosmology's deepest mysteries, but the devil lurked in the details. Guth's original inflation model had a fatal flaw. The phase transition happened too quickly, leaving the universe empty and cold instead of hot and dense. Within months, other physicists, including Andre Linde, Andreas Albrecht and Paul Steinhardt, developed improved versions that fix these problems. Andre Linde, working independently in the Soviet Union, developed what he called chaotic inflation. His version did not require a phase transition at all. Instead, the inflaton field simply started with a large value and slowly rolled down its potential energy curve. As long as the potential was flat enough, inflation would occur naturally. This was more robust than Guth's original version and worked for a wider range of initial conditions. Albrecht and Steinhardt, working together at the University of Pennsylvania, developed new inflation using ideas about supercooling and bubble nucleation. Their model allowed the false vacuum to tunnel through the potential barrier more slowly, giving inflation time to homogenize the universe before reheating occurred. These refinements transformed inflation from an intriguing idea with technical problems into a viable cosmological paradigm. The refined model worked like this. In the earliest moments after the Planck epoch, the universe was filled with a quantum field called the inflaton. This field had a peculiar property. Unlike normal matter, whose energy density decreases as space expands, the inflaton's energy density remained nearly constant. As space expanded, more inflaton energy appeared, maintaining the same density. This defied common sense, but not the laws of physics. Quantum fields can have this property if their potential energy dominates over their kinetic energy. The physics behind this strange behavior comes from general relativity. Einstein's field equations relate the geometry of space-time to the energy and momentum content of matter and fields. For normal matter, pressure is positive and small compared to energy density. But quantum fields in excited states can have negative pressure. The false vacuum state of the inflaton has negative pressure equal in magnitude to its positive energy density. This creates a negative pressure term in Einstein's equations that drives acceleration rather than deceleration. The inflaton field sat in what physicists call a false vacuum state, a local minimum of energy but not the true minimum. Like a ball resting in a small depression on a hillside rather than at the bottom of the valley, the false vacuum was stable temporarily but wanted to decay to a lower energy. While in this false vacuum state, the inflaton's energy density acted as a cosmological constant, driving exponential expansion through the equations of general relativity. This expansion was violent beyond comprehension. In less than 10 to the power of negative 32 seconds, the universe expanded by a factor of at least 10 to the power of 26. Some models predict expansion factors of 10 to the power of 50 or higher, a region smaller than a proton inflated to larger than the observable universe. Space expanded faster than the speed of light, which is permitted because nothing was moving through space. Space itself was growing. Then the inflaton decayed. The false vacuum transitioned to the true vacuum, and all that potential energy converted into radiation and particles. The universe reheated to tremendous temperatures. This reheating phase connected inflation to the standard Big Bang cosmology. Everything that happened after reheating, the formation of atomic nuclei, the decoupling of light from matter, the gravitational collapse of the first stars, proceeded according to well-understood physics. Inflation set the initial conditions that the Big Bang then evolved. But inflation did more than solve cosmological puzzles. It provided a mechanism for structure formation. The inflaton field, like all quantum fields, experienced quantum fluctuations. These fluctuations were microscopic and random. But during inflation, they were stretched to cosmic scales. Tiny quantum jitters became macroscopic density variations spanning billions of light years. These variations seeded the formation of galaxies. Every structure we observe in the universe, every galaxy cluster, every star, every planet, traces its ancestry to quantum fluctuations inflated to astronomical sizes. The evidence for inflation has mounted steadily. The cosmic microwave background shows patterns of temperature fluctuations that precisely match inflation's predictions. The spectrum of these fluctuations, how their amplitude varies with scale, agrees with inflationary models to remarkable precision. The universe's flatness, measured through multiple independent methods, confirms inflation's prediction that geometry should be Euclidean. Inflation has transformed from a speculative idea to the leading paradigm in cosmology. Yet inflation raises new questions, even as it answers old ones. Where did the inflaton field come from? What set its initial value? Why did it have the right properties to drive inflation? These questions push us back toward the fundamental mystery of origin. And here, quantum cosmology offers provocative answers. In 1983, James Hartle and Stephen Hawking published a paper with an audacious proposal. What if the universe has no boundary in time? What if asking what came before the Big Bang is meaningless not because time began there, but because time transforms into something else? Their idea required using imaginary time. In mathematics, imaginary numbers are multiples of the square root of -1. They seem like abstract constructs, but they appear naturally in quantum mechanics. The Schrödinger equation, which governs quantum systems, uses imaginary numbers fundamentally. Hartley and Hawking suggested applying this mathematical trick to time itself. In imaginary time, the distinction between time and space blurs. The 4 dimensions of space-time become indistinguishable. This four-dimensional space has no boundary and no singularity. The universe does not begin at a point. Instead, as you trace backward in time toward the Big Bang, time becomes more and more space-like. The Big Bang is not a moment of creation, but the southern pole on a sphere. Just as asking what is south of the South Pole is meaningless, because the concept of south dissolves at the pole, asking what happened before the Big Bang is meaningless, because the concept of before dissolves at the origin. This proposal is mathematically elegant but conceptually challenging. What does it mean for time to become imaginary? Hartley and Hawking argued that imaginary time is the fundamental reality, and what we perceive as real time is a derivative concept that emerges from quantum cosmology. In imaginary time, the universe is finite but unbounded, like the surface of a sphere. In real time, the universe has a beginning but no first moment, like the sequence of positive numbers approaching zero but never reaching it. The no-boundary proposal connects to the Wheeler-DeWitt equation, a quantum mechanical equation for the wave function of the universe. In standard quantum mechanics, the Schrödinger equation describes how a system's wave function evolves in time. But the Wheeler-DeWitt equation is timeless. It describes the quantum state of the entire universe, but does not include time as a parameter. This seems paradoxical. How can you describe evolution without time? The resolution is that time is not fundamental in quantum gravity. Time is an emergent property that arises from the quantum state of the universe. The Wheeler-DeWitt equation describes all possible three-dimensional spatial geometries that the universe could have, and their quantum amplitudes. From this timeless description, the familiar notion of time flowing forward emerges as a semi-classical approximation, in regions where the wave function is sharply peaked. The wave function of the universe, often denoted by the Greek letter SI, contains all information about the cosmos. Its squared amplitude gives the probability of finding the universe in a particular configuration. The Hartle-Hawking no-boundary proposal provides specific boundary conditions for this wave function. It says we should calculate PSI by summing over all compact 4 geometries that match the observed three-dimensional geometry of our universe. This sum is a path integral, the same mathematical tool Feynman developed to calculate quantum mechanical probabilities. In this picture, the universe does not tunnel from nothing into existence at a singular moment. Instead, the universe's wave function is a superposition of all possible geometries that smoothly close off in imaginary time. Some of these geometries resemble our universe, others are wildly different. The path integral sums over all of them, weighted by their quantum amplitude. Our universe emerges as the most probable configuration, the one with the largest quantum amplitude in the path integral. This proposal has profound implications. The universe requires no external cause. It exists as a quantum mechanical entity whose wave function is determined by the laws of physics alone. The question of what came before the Big Bang dissolves because there is no before. Time itself is part of the universe, not a background in which the universe exists. Creation becomes a quantum process, probabilistic rather than deterministic, governed by the Wheeler-DeWitt equation rather than classical causation. Critics have raised objections. The path integral in quantum gravity is notoriously difficult to define rigorously. Different approaches to quantizing gravity yield different predictions. The no-boundary proposal makes the universe's wave function complex-valued, which raises questions about the interpretation of probability, and the proposal requires choosing specific boundary conditions that seem arbitrary. Why should we sum over only compact geometries? Why not include other topologies? Despite these challenges, the Hartle-Hawking proposal represents a milestone in thinking about cosmic origins. It demonstrates that quantum mechanics allows for universes to exist without requiring an external creator or a pre-existing stage on which creation unfolds. The universe can be self-contained, finite in imaginary time but unbounded, requiring nothing external to explain its existence. Yet another approach to the quantum origin of the universe offers a different perspective. Instead of smoothly closing off in imaginary time, what if the universe tunneled into existence from literally nothing? Alexander Vilenkin took a more radical approach. In 1982, he proposed that the universe began as a quantum tunneling event from absolutely nothing. Not from a quantum vacuum filled with fields and fluctuations, not from a pre-existing geometry, from nothing at all. This sounds absurd. How can something tunnel from nothing when there is no space for it to tunnel through, no time for tunneling to occur in? Vilenkin's answer relied on the probabilistic nature of quantum mechanics. In quantum theory, transitions between states do not require continuous paths. A particle can simply appear in a classically forbidden region without having traversed the space between. This is quantum tunneling in its purest form. Vilenkin proposed that the universe began as a quantum tunneling event from a state with no space and no time to a state with both. The initial state is not a vacuum in the usual sense. It is true nothingness, the absence of everything, including the laws of physics. The final state is a small, closed universe containing space, time, and energy. The transition between these states requires no prior cause, because causation itself does not exist until after the tunneling event. The mathematics of this proposal involves solving the Wheeler-DeWitt equation with specific boundary conditions. Vilenkin chose boundary conditions corresponding to a wave function that has no incoming waves. In quantum mechanics, scattering processes involve incoming waves representing the initial state and outgoing waves representing possible final states. Vilenkin's boundary condition says there is no initial state, only outgoing waves representing the universe emerging from nothing. This approach makes a startling prediction. The universe that tunnels into existence is not static. It immediately begins inflating. The tunneling event naturally creates the conditions necessary for inflation to occur. The universe is born in an excited state, with the inflaton field sitting high up its potential energy curve. This excited state drives exponential expansion, connecting Vilenkin's tunneling proposal directly to inflationary cosmology. The tunneling probability can be calculated using semi-classical approximation methods. The result depends on the details of the matter, content, and geometry, but for many models, the probability is not zero. The universe can spontaneously appear from nothing with a finite probability. This probability is extraordinarily small when expressed in conventional units. But in quantum cosmology, probability has a different meaning. The wave function describes the quantum state without reference to an external observer performing measurements. The universe does not need to win a lottery to exist. It simply exists as one possible solution to the Wheeler-DeWitt equation. Critics have objected that Vilenkin's nothing is not truly nothing. The Wheeler-DeWitt equation itself represents a law of physics. The Hilbert space of quantum states exists as a mathematical structure. Can we really call this nothing? Vilenkin responded that these are not physical entities that exist in space and time. They are logical structures, patterns of mathematics. The laws of physics are not things that exist. They are descriptions of how things that do exist behave. In this sense, the tunneling proposal truly starts from nothing physical and explains how something physical comes into being. Another objection concerns energy conservation. Where does the energy of the universe come from? If it appears from nothing, doesn't this violate conservation of energy? The answer is subtle. In general relativity, the total energy of a closed universe can be exactly zero. The positive energy of matter and radiation is balanced by the negative gravitational potential energy. This is not a coincidence. It is a consequence of the way gravity works. As the universe expands, both types of energy grow in magnitude, but their sum remains zero. The universe is the ultimate free lunch, as physicist Alan Guth memorably put it. This zero energy property makes the tunneling proposal more plausible. The universe does not need to borrow energy from anywhere. It can appear from nothing without violating conservation laws because its total energy is zero. Every particle and photon comes with a corresponding debt of gravitational potential energy. The books balance exactly. Vilenkin's tunneling proposal and Hartley-Hawking's no-boundary proposal represent two different ways of thinking about the same deep question. They make different mathematical assumptions and arrive at different physical pictures, yet both share a common theme. The universe can begin without requiring anything external to explain its beginning. Quantum mechanics allows for spontaneous creation. The boundary between being and non-being becomes fuzzy and probabilistic rather than sharp and deterministic. But if quantum mechanics allows one universe to tunnel into existence, why not many? This question leads us to one of the strangest ideas in modern cosmology. Imagine inflation beginning in a small patch of space. The inflaton field drives exponential expansion, but inflation does not end everywhere simultaneously. Quantum fluctuations in the inflaton field create regions where inflation continues while neighboring regions end. The regions still inflating expand exponentially, quickly dwarfing the regions where inflation has ended. These inflating regions themselves contain quantum fluctuations that create new patches where inflation continues even as it ends elsewhere. This process has no natural stopping point. Once inflation starts in any region, it produces more inflating regions faster than they can decay. The volume of inflating space grows without bound. Inflation becomes eternal, continuing forever into the future even though it ends in particular locations. This is eternal inflation, first described by Paul Steinhardt and Alexander Vilenkin in 1983. The mechanism driving eternal inflation is subtle, but powerful. Consider an inflating region where the inflaton field is slowly rolling down its potential energy curve toward the minimum where inflation ends. Quantum fluctuations cause the field value to jump randomly up and down as it rolls. In most of the volume, the downward classical rolling dominates and inflation ends. But in some regions, an upward quantum fluctuation pushes the field back up the potential. These regions where quantum fluctuations win continue inflating, and here is the key. They inflate so fast that even though they occupy a small fraction of the volume at any moment, they quickly dominate the total volume. An inflating region doubles in size every tiny fraction of a second. Even a 1% probability that inflation continues in a given region is enough to ensure that inflating volume grows faster than it decays. Think of it like compound interest. If your investment grows at 10% per year and you reinvest the profits, your wealth grows exponentially. Similarly, inflating regions produce more inflating regions, and those produce still more, creating exponential growth of inflating volume. This runaway process continues indefinitely. Inflation, once started, never completely stops. Eternal inflation transforms our picture of reality radically. The region where inflation ended and our familiar universe formed is just one bubble in an infinite foam of universes. Each bubble is causally disconnected from the others. They are separated by exponentially expanding regions still undergoing inflation. To an observer in any bubble, their universe appears self-contained and possibly infinite. But from a global perspective, it is just one pocket universe in an eternally inflating multiverse. The eternally inflating space between pocket universes is sometimes called the inflaton sea or the multiverse foam. It is not static, but dynamically expanding at breakneck speed. New pocket universes nucleate from this background like bubbles forming in boiling water. Each bubble expands at the speed of light in its own reference frame, but the space between bubbles expands faster than light, ensuring they never collide in most models. Each pocket universe can have different properties. The inflaton field may decay differently in different bubbles, leading to different physics. In the context of string theory, this diversity becomes even more extreme. String theory attempts to unify all forces, including gravity, by replacing point particles with tiny vibrating strings. The theory requires extra spatial dimensions beyond the three we experience. These extra dimensions must be compactified, curled up so small we cannot detect them. String theory emerged in the 1960s as an attempt to understand the strong nuclear force. Physicists discovered that certain scattering amplitudes could be described by vibrating strings rather than point particles. Initially, this seemed to work only for strongly interacting particles, but anomalies and inconsistencies plagued the theory. Then in 1984, the first superstring revolution showed that the theory could incorporate all forces, including gravity, if formulated in 10 dimensions. The extra 6 dimensions must be compactified on a Calabi-Yau manifold, a special type of geometric space with particular symmetries. The shape of this manifold determines what particles and forces appear in our 4-dimensional world. Different shapes yield different physics, and here is where things become almost absurdly complex. The problem, or perhaps the feature, is that there are approximately 10 to the power of 500 different ways to compactify the extra dimensions. Each choice yields a different effective physics in our 3-dimensional world. Different particles, different force strengths, different cosmological constants. This vast space of possibilities is called the string landscape. It is not a physical landscape, but a metaphorical one, a high-dimensional space of possible theories. This number, 10 to the power of 500, is so large it defies comprehension. For comparison, there are about 10 to the power of 80 atoms in the observable universe. The number of possible string theory vacua exceeds the number of atoms by a factor so enormous there are not enough atoms in the universe to write it out. Each vacuum represents a different possible universe with its own laws of physics. The string landscape includes vacua with different numbers of dimensions that remain large, different particle content, different gauge groups describing the forces, and different values for coupling constants and masses. Some vacua would have universes that recollapse immediately. Some would expand so fast that no structures could form. Some would have no atoms because electrons and protons would not bind. The landscape is vast and mostly hostile to life. Leonard Susskind combined eternal inflation with the string landscape to create a bold hypothesis. Each pocket universe in the eternally inflating multiverse realizes a different point in the string landscape. All possible string theories are actualized somewhere in the multiverse. Our universe is just one possibility among an essentially infinite number of others. The mechanism connecting eternal inflation to the string landscape involves quantum tunneling between different vacua. A pocket universe might start in one vacuum state, corresponding to one point in the landscape. Quantum fluctuations could cause it to tunnel to a different vacuum with different physics. This tunneling process continues throughout the multiverse, sampling the entire landscape. Different vacua have different vacuum energies, and therefore different rates of inflation. Some inflate rapidly and dominate the volume, others inflate slowly or not at all. The statistical distribution of pocket universes across the landscape depends on these factors. Vacua that inflate faster produce more daughter universes, and therefore become more common in the multiverse, even if they started as rare events. This multiverse hypothesis has generated intense controversy. Proponents argue it explains the apparent fine-tuning of physical constants in our universe. The cosmological constant, the energy density of empty space, has a value that appears absurdly small yet critically important. If it were much larger, the universe would have expanded too quickly for galaxies to form. If it were negative, the universe would have recollapsed before stars could ignite. The value appears fine-tuned for life. The cosmological constant problem is actually two problems in one. First, why is the vacuum energy not enormous? Quantum field theory predicts it should be about 10 to the power of 120 times larger than observed. Every quantum field contributes to vacuum energy, and the sum of all contributions should be huge. Yet we measure a tiny value, consistent with 0 to high precision, until dark energy observations in the late 1990s showed it is small but non-zero. Second, why does the cosmological constant have a value comparable to the current matter density? This is the coincidence problem. Throughout most of cosmic history, vacuum energy was negligible compared to matter and radiation. Only in recent billions of years has it come to dominate. We happen to live at the special time when vacuum energy and matter density are comparable. Why? In a single universe, this fine-tuning seems to require an explanation. Why this value and not another? The multiverse provides an answer. All values occur somewhere. We observe a life-permitting value because we could not exist in universes with different values. This is an application of the anthropic principle. The properties we observe are selected by the fact of our existence rather than being determined by fundamental principles. Critics object that the multiverse hypothesis is unfalsifiable. If other universes are causally disconnected from ours, we cannot observe them directly. Any apparent fine-tuning can be explained away by invoking the multiverse without making testable predictions. This, critics argue, removes cosmology from the realm of science and makes it metaphysics or even theology. Defenders respond that the multiverse is not a hypothesis we invented to solve problems. It is a prediction of our best theories. Inflation naturally becomes eternal under plausible conditions. String theory naturally predicts a landscape of possibilities. We did not choose these features. They emerge from mathematics we developed to explain other phenomena. If our theories predict a multiverse, we should take that prediction seriously even if the multiverse cannot be directly observed. Moreover, the multiverse may make testable predictions. If eternal inflation is correct, we should find ourselves in a typical pocket universe, not an exceptional one. This leads to probabilistic predictions about what we should observe. The distribution of pocket universes in the multiverse affects what kinds of universes are typical. By measuring properties of our universe precisely, we can test whether they match the typical values predicted by multiverse models. Some physicists have proposed that collisions between pocket universes might leave imprints in the cosmic microwave background. If our universe collided with another bubble during or shortly after inflation, The collision could create patterns of temperature fluctuations observable today. Several groups have searched for these signatures. So far, no compelling evidence has been found, but the search continues. The philosophical implications are staggering. If the multiverse exists, our universe is not special. Everything that can happen does happen somewhere. Every possible arrangement of matter allowed by physics, every possible history, every possible configuration of atoms and energy exists in some pocket universe. Somewhere in the multiverse, there is a universe identical to ours except one atom is displaced by a nanometer. Somewhere there is a universe where you made different choices. The multiverse contains all possibilities. This raises questions about probability and prediction. In an infinite multiverse, anything that can happen will happen infinitely many times. How do we calculate the probability of any observation when there are infinite instances of that observation? This is the measure problem in cosmology, a deep technical challenge that remains unsolved. Different proposals for defining probability measures in eternal inflation lead to different predictions, and we do not know which, if any, is correct. Stephen Hawking's final paper, published posthumously with Thomas Hertog, argued that the traditional picture of eternal inflation is wrong. They claimed that quantum effects make the multiverse finite rather than infinite. Their formulation predicts a universe that is complex but not infinitely varied. This would make the theory more testable by reducing the number of possible outcomes. The multiverse hypothesis transforms the question of cosmic origins. Instead of asking why this universe exists, we ask why any universes exist. The answer may be that universes exist because the laws of physics, or perhaps meta-laws governing the string landscape, allow for their existence. In this view, existence is the default state. Non-existence would require explanation. But this pushes the question back one more level. Why these laws? Why this landscape? Why does anything obey mathematical structure at all? Here we approach the boundary of science. Yet even here, physics offers one more perspective on creation from nothing. Not all cosmologists embrace inflation and the multiverse. Alternative models attempt to explain cosmic origins through different mechanisms. One of the most intriguing is Roger Penrose's conformal cyclic cosmology. Penrose, who won the Nobel Prize in 2020 for his work on black holes, proposes that the Big Bang was not the beginning of time, but a transition between two infinite phases. In the far future, our universe will expand forever, approaching a state of maximum entropy. All stars will burn out. Black holes will evaporate through Hawking radiation. Only radiation remains, spreading out across infinite space. Penrose noticed a mathematical connection between this far future state and the Big Bang. Both involve radiation in a nearly perfect thermal equilibrium. Both have no characteristic length scale. In the Big Bang, everything is compressed to a point. In the far future, everything is stretched to infinity. But mathematically, these two states can be conformally mapped to each other. They are equivalent up to a rescaling. Penrose proposes that this is not coincidence but a real physical connection. The infinite future of one universe becomes the Big Bang of the next. Time is cyclic on a cosmic scale. Each universe goes through a complete life cycle. It begins hot and dense, expands and cools, forms structures, reaches maximum entropy as those structures decay, then smoothly transitions into the Big Bang of the next cycle. This process continues endlessly into the past and future. The appeal of this model is that it eliminates the beginning. There is no first moment. Time extends infinitely in both directions. The question of why there is something rather than nothing dissolves because there has always been something. Creation from nothing never happens because nothing never was. Penrose has searched for evidence of conformal cyclic cosmology in the cosmic microwave background. He claims to have found circular patterns that could be rings created by colliding black holes in the previous universe. These rings would be imprinted on the sky when the previous universe transitioned into ours. Other cosmologists have disputed these findings, arguing that the patterns are consistent with random fluctuations. The debate continues. Another cyclic model comes from loop quantum cosmology. Loop quantum gravity attempts to quantize space-time itself by replacing continuous space with discrete loops of quantum geometry. In this framework, the Big Bang singularity is replaced by a big bounce. The universe contracts from a previous phase, reaches a minimum size determined by quantum gravity effects, then bounces back into expansion. The bounce avoids the singularity by invoking quantum mechanical repulsion. As matter density increases during contraction, quantum effects create an effective repulsive force that halts the collapse and reverses it into expansion. The mathematics shows that this bounce is generic in loop quantum cosmology. It does not require fine-tuning or special conditions. Loop quantum cosmology makes testable predictions. The bounce leaves signatures in the primordial power spectrum of density fluctuations. These signatures differ from those predicted by inflation. Future observations of the cosmic microwave background with greater sensitivity could distinguish between the models. Ekpyrotic models propose yet another alternative. These models invoke higher dimensional brains, membranes extending through extra dimensions predicted by string theory. Our universe is a three-dimensional brain embedded in higher dimensional space. The Bang resulted from a collision between our brain and another parallel brain. The collision released enormous energy, creating the hot, dense state we call the Big Bang. Ekpyrotic models can be cyclic or one-time events. In cyclic versions, the brains collide repeatedly, bouncing apart then falling back together in an endless cycle. Each collision creates a new Big Bang. Between collisions, the universe expands and cools. These models attempt to solve cosmological problems without invoking inflation by generating density fluctuations through brain dynamics instead. All these alternative models share a common feature. They attempt to avoid the question of absolute beginning by making time extend infinitely into the past in some form. Either through cycles, bounces, or smooth transitions, they propose that the universe has always existed in some state. Creation from nothing is avoided by denying that nothing ever existed. Yet these models face challenges. The Bordguth-Vilenkin theorem, proven by Arvind Borda, Alan Guth, and Alexander Vilenkin in 2003, shows that any universe that has been expanding on average throughout its history must have had a beginning. This includes eternally inflating universes and most cyclic models. The theorem demonstrates that eternal expansion into the past is impossible. At some point, classical spacetime breaks down and quantum gravity becomes essential. This does not necessarily vindicate inflation over alternatives. It simply demonstrates that we cannot avoid confronting the question of cosmic origins by appealing to an infinite past. Even if time extends infinitely backward in some formal sense, there must be a boundary where our current physics fails. Beyond that boundary, we need quantum cosmology, and in quantum cosmology, the question transforms from what happened before the beginning to what is the quantum state of the universe. All these theoretical proposals, from inflation to quantum tunneling to the multiverse, might seem like pure speculation divorced from observational reality. But remarkably, we have evidence for many of these ideas. The cosmic microwave background has become the Rosetta Stone of cosmology, allowing us to read the history written in the sky. The Planck satellite, launched by the European Space Agency in 2009, mapped the cosmic microwave background with unprecedented precision. The temperature variations across the sky, tiny fluctuations of about 1 part in 100,000, encode information about the early universe. These fluctuations are not random noise. They have a specific statistical pattern predicted by inflation. The pattern appears as peaks in the power spectrum, which shows how much temperature variation exists at different angular scales on the sky. The first peak corresponds to the largest sound waves in the primordial plasma. The second peak corresponds to waves with half that wavelength, the third peak to 1/3 the wavelength, and so on. These acoustic peaks arise from sound waves bouncing back and forth in the plasma before atoms formed and light decoupled. Inflation predicts that these peaks should exist at specific locations with specific heights. The predictions match observations with stunning accuracy. The first peak appears exactly where inflation says it should. The relative heights of the peaks match predictions. The slight tilt in the spectrum, the way fluctuations vary with scale, agrees with inflationary models. This is not one lucky guess, but a detailed pattern that inflation predicted before it was measured. Moreover, the fluctuations are nearly scale invariant, meaning they have similar amplitude at different scales. This scale invariance is a hallmark of quantum fluctuations stretched by inflation. If structure had formed through other mechanisms, we would expect different statistical properties. The observations favour inflation over alternatives. The polarization of the cosmic microwave background provides additional evidence. Light waves oscillate perpendicular to their direction of travel. Polarization measures the direction of this oscillation. Scattering in the early universe creates polarization patterns that depend on the density and velocity of matter at decoupling. These patterns, measured with exquisite precision, match inflationary predictions. Gravitational waves from the inflationary epoch would create a specific type of polarization pattern called B-modes. In 2014, the BSEP-2 experiment announced detection of these B-modes, which would have been smoking gun evidence for inflation. The announcement generated enormous excitement. Alan Guth appeared on news programs worldwide, but subsequent analysis showed the signal was contaminated by dust in our galaxy. The primordial B-modes remained undetected, though searches continue. Even without definitive B-mode detection, the totality of evidence strongly supports inflation. No other theory explains the flatness of space, the uniformity of the cosmic microwave background, the absence of magnetic monopoles, and the detailed statistics of temperature fluctuations simultaneously. Inflation is not proven, but it is the leading paradigm because it explains so much with so little. The evidence for quantum mechanics at cosmological scales is more indirect but equally compelling. The temperature fluctuations we observe originated as quantum fluctuations in the inflaton field. These microscopic quantum jitters, stretched to cosmic scales by inflation, seeded all the structure we see. Every galaxy cluster, every galaxy, every star traces its lineage to quantum uncertainty made manifest. This is profound. Quantum mechanics usually affects only the microscopic world. An electron can be in two places at once. A photon can interfere with itself. But these effects average out for macroscopic objects. You never observe a chair in a quantum superposition. Yet the universe itself underwent quantum fluctuations when it was subatomic in size. Those fluctuations were stretched to astronomical scales while remaining quantum in origin. We see the fingerprints of quantum mechanics imprinted on the largest structures in the cosmos. The cosmic web of galaxies, the distribution of matter throughout space, the clustering of galaxy clusters, all of this traces back to quantum field theory operating at the Planck scale during inflation. We can calculate what pattern of fluctuations quantum mechanics should produce. We can evolve those fluctuations forward in time using gravity and hydrodynamics. The predicted distribution of galaxies today matches what we observe. Quantum mechanics explains the architecture of the universe. We have journeyed to the edge of physics, examining multiple proposals for how the universe could begin from nothing. Quantum tunneling from vacuum states, the Hartle-Hawking no-boundary proposal, eternal inflation creating infinite pocket universes, cyclic cosmologies avoiding absolute beginnings. Each approach reveals something profound about the nature of existence itself. But now, we must ask the deeper question that lurks beneath all these scientific proposals. Have we truly explained something from nothing, or have we simply redefined nothing into a something we can calculate with? The quantum vacuum is not empty. We have seen this demonstrated through the Lamb shift, the Casimir effect, Hawking radiation, and vacuum energy density. It seethes with virtual particles that pop in and out of existence. It contains energy density that curves space-time. It obeys physical laws that determine how it behaves. Is this nothing? Philosophers would argue emphatically that it is something, even if it contains no actual particles at any given moment. The laws of quantum mechanics are not nothing. The mathematical structure of Hilbert space is not nothing. The quantum fields that permeate space are not nothing. Even if no matter exists, the stage on which matter could appear is already something, and that something requires explanation. Lawrence Krauss wrote a popular book titled A Universe from Nothing, arguing that modern physics has solved the age-old philosophical question. But philosopher David Albert reviewed it harshly in the New York Times, pointing out a fundamental flaw in Krauss's argument. Krauss's nothing, Albert argued, is not really nothing in the philosophical sense. It is a quantum vacuum state governed by laws of physics existing in some kind of space-obeying mathematical rules. True, nothing would include no laws, no fields, no space, no time, no mathematical structures, no logical principles, no potential for anything whatsoever. Absolute nothing. Complete absence. Total non-being. Can physics explain how existence emerges from this absolute nothing? Perhaps not, and here is why. The Wheeler-DeWitt equation, the Hartle-Hawking proposal, Vilenkin's tunneling scenario all assume the existence of quantum mechanics as a framework. They assume mathematics describes reality. They assume logical consistency and the principle of sufficient reason. They assume Hilbert spaces exist as mathematical structures and wave functions evolve according to equations. These assumptions are not physical entities existing in space and time. They are metaphysical commitments, foundational principles that cannot themselves be proven by physics because physics requires them as foundations. This leads to a deep philosophical question that may be unanswerable within science. Why is there something rather than nothing? We can answer this question at multiple levels, each level pushing the question back to a deeper foundation. Physics can explain how this universe emerged from a quantum state at the Planck epoch. Cosmology can explain how that quantum state evolved according to the Wheeler-DeWitt equation, or underwent inflationary expansion driven by the inflaton field. But why do those laws exist? Why does the Wheeler-DeWitt equation have the specific form it does rather than some other form? Why does mathematics describe reality at all? Why is there logical structure instead of pure chaos or perfect absence? Here we reach the boundary of science, the limit beyond which empirical investigation cannot proceed. Science can explain how one thing leads to another, within a framework of natural laws. It excels at finding mechanisms, tracing causal chains, predicting future states from initial conditions, but it cannot explain why natural laws exist in the first place without invoking something outside the system of nature, and once you invoke something outside nature, you have left science behind and entered metaphysics or theology. Some philosophers argue that existence requires no explanation. They claim that nothing is unstable in a deep sense. Given enough time, given infinite possibilities, something would inevitably appear from nothing through quantum fluctuations, and once something exists, it can evolve and complexify according to physical law. But this argument has fatal flaws. It assumes time exists before the universe, which seems wrong since time began at the Big Bang. It assumes quantum mechanics with its fluctuations and probabilities, which is part of the something that needs explaining. It assumes mathematical possibility, logical structure, and the principle that what can happen will happen, all of which are somethings rather than nothings. David Hume argued in the 18th century that we should not expect to find ultimate explanations for existence. Every attempt to explain something invokes prior causes or more fundamental principles, creating an infinite regress that never reaches bedrock. At some point, we must accept brute facts, unexplained explainers, foundations that simply are without further justification. For Hume, the universe itself might be such a brute fact. It exists, and asking why it exists makes no more sense than asking why logical principles are logical or why mathematics is mathematical. Gottfried Leibniz took the opposite view. He argued that the principle of sufficient reason demands that everything has an explanation for why it is rather than is not. This includes the universe as a whole. Leibniz concluded that the explanation must be found in a necessary being, something that exists by its own nature and could not fail to exist. This necessary being, which he identified with God, serves as the ultimate foundation that requires no further explanation because necessity is built into its essence. But this merely pushes the question back. Why is necessary existence possible? Why should there be any necessary being rather than absolute nothing? What determines that some things exist necessarily while others exist contingently? The mystery of being versus non-being remains, relocated to a different level but not resolved. Contemporary philosophers like Derek Parfit have wrestled extensively with these questions. In his monumental work, Why Anything, Why This?, Parfit examined every proposed answer to the question of existence and found them all wanting in various ways. Some answers invoke infinite regress, some invoke brute facts, some invoke necessary beings, some deny the question is meaningful, but none provides a fully satisfying explanation that eliminates all mystery and answers all objections. Parfit considered the possibility that all possible universes exist, actualized in some vast multiverse. In this view, existence is maximal. Everything that can exist does exist somewhere in the ensemble of realities. Our universe is just one possibility among infinity. This everything exists hypothesis has a certain logical appeal. If existence is the default and non-existence requires explanation, then perhaps all possibilities are actualized because there is no principle selecting some over others. But this raises new questions. Why should logical possibility translate into actual existence? Many things are logically possible, meaning they involve no contradiction, but that does not mean they actually exist. A golden mountain is logically possible but does not exist anywhere in our universe. Even if we grant that all possibilities exist in some grand multiverse, we still must explain why possibility itself exists, why there is a space of logical possibilities rather than no space at all. The anthropic principle offers a different perspective on our existence and the properties of our universe. We observe a universe that permits our existence, that allows complex chemistry, that enables the formation of stars and planets, and eventually life, because we could not exist in any universe that does not permit observers. The properties of our universe appear fine-tuned for life. Change the strength of gravity slightly and stars cannot form. Change the mass of the electron and chemistry becomes impossible. Change the cosmological constant and galaxies never condense from the primordial plasma. In a multiverse containing all possible configurations of physical laws, most universes are sterile, devoid of complexity and incapable of supporting life. We observe the rare type that permits observers because we are observers. This selection effect is statistical. It does not require design or purpose. It is simply a consequence of the fact that observations require observers, and observers require observer-permitting conditions. This explanation is unsatisfying to many physicists and philosophers. It seems to abandon the search for deeper understanding, replacing fundamental explanations with anthropic reasoning. Why should the existence of observers be taken as a fundamental explanatory principle? It feels circular, almost tautological. We exist because the universe permits existence. The universe permits existence because we exist to observe it. Where is the real explanation? What are we actually learning by invoking the anthropic principle? Steven Weinberg, Nobel laureate in physics, has argued that the anthropic principle, while frustrating, may be the only explanation available for some features of the universe. The cosmological constant problem, the enormous discrepancy between calculated and observed vacuum energy, might have no other solution. If all values appear in different pocket universes of an eternal inflationary multiverse, we inevitably find ourselves in one where the value permits galaxy formation and thus life. This is not the answer physicists wanted. They wanted to calculate the cosmological constant from first principles, but nature may not care what physicists want, yet perhaps we must accept some level of circularity or brute fact at the foundation of existence. Every explanatory chain terminates somewhere, and that termination can take only a few forms, either in an infinite regress of causes that explains nothing because we never reach a foundation, or in a circular structure where A explains B, B explains C, and C explains A, which also explains nothing because we never escape the circle, or in a brute fact something that simply is without further explanation, or in a necessary being whose existence requires no explanation because necessity is part of its essence. Modern physics has shown that the question, how did everything begin from nothing, may not have the form we expect based on everyday intuition. The universe might have no beginning in time. It might emerge from a quantum state that is timeless, a wave function that exists outside temporal flow. It might be eternal in some sense even if our local pocket universe had a temporal origin. Time itself might be an emergent property rather than a fundamental aspect of reality, something that arises from quantum entanglement or thermodynamic processes rather than being woven into the fabric of existence from the start. Moreover, the concept of nothing has dissolved under quantum mechanical scrutiny into something far more complex than simple absence. Perfect nothingness may be impossible according to the laws of physics. The quantum vacuum has structure and energy that cannot be eliminated. Even space itself may be an emergent phenomenon, arising from more fundamental quantum degrees of freedom, not a stage on which physics plays out, but a consequence of quantum correlations and entanglement. What we call nothing, the supposedly empty vacuum of space devoid of particles, may be a particular excited state of something deeper. In some formulations of quantum gravity, space emerges from the entanglement structure of quantum information. In string theory, space may arise from the properties of strings and branes in higher dimensions. In loop quantum gravity, space is woven from networks of quantum geometries. In all these approaches, space is not fundamental. It is derived, emergent, contingent on something more basic. The role of consciousness and observation in quantum mechanics remains controversial and potentially relevant to questions of cosmic origins. Some interpretations of quantum mechanics grant observers a special role in collapsing wave functions and actualizing potential states. In the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, the wave function exists in superposition until measurement forces it to actualize a definite value. But what counts as measurement? Does it require consciousness? In this view, the universe requires observers to exist fully and definitely, rather than remaining in quantum superposition. But who observed the early universe before life emerged? This paradox has led to various proposals. Some argue that the universe is a self-observing quantum system, where subsystems measure each other without requiring external consciousness. Others propose that consciousness plays no special role in quantum mechanics, despite appearances, and decoherence through interaction with environments suffices to actualize definite states. Still, others suggest that observation retroactively creates the past, with later observers actualizing earlier states through a kind of backwards causation. John Wheeler proposed a participatory universe where observers play a fundamental role in bringing reality into existence. In his delayed choice experiment, he showed that observer decisions made in the present seem to determine what happened in the past. Photons behave as waves, or particles depending on how we choose to measure them, even if we make that choice after the photon has already passed through the experimental apparatus. Wheeler speculated that observers in the far future might retroactively actualize the entire history of the universe through their observations. These ideas push quantum mechanics to its limits and beyond, into territory where science blends with philosophy and speculation. Most physicists reject the notion that consciousness is fundamental to quantum mechanics. They argue that decoherence and many worlds interpretation or other approaches that don't require wave function collapse explain observations without invoking observers as special. But minority views persist, and the questions remain genuinely open more than 90 years after quantum mechanics was formulated. What we have learned through modern cosmology and quantum physics is nonetheless remarkable and transformative. The universe can emerge from quantum states without requiring external causes or violations of physical law. The laws of physics permit creation from quantum vacuum states. The boundary between existence and non-existence is fuzzy and probabilistic rather than sharp and absolute. Time itself may begin with the universe rather than being a stage on which the universe appears. Space-time may be emergent rather than fundamental. Most profoundly, we have learned that nothingness is not the natural default state of reality. Existence may be more stable, more natural, more fundamental than non-existence. The quantum vacuum cannot remain empty. Virtual particles must appear and disappear constantly, forbidden from perfect stillness by the uncertainty principle. Quantum fields must fluctuate. In a quantum universe, perfect emptiness and perfect stillness are violations of the uncertainty principle. Something is required by the laws of physics. Nothing is forbidden. This does not fully explain why there is something rather than nothing. It transforms the question and pushes it back to why quantum mechanics exists and why it has the specific properties it does. But it represents genuine philosophical and scientific progress. We understand how our universe could begin without violating physical laws. We understand the mechanisms by which nothing, in the quantum sense of vacuum state, becomes something in the form of matter and energy in space-time. We understand that creation is not a violation of nature but a consequence of nature's deepest principles. The question of ultimate origins may forever remain beyond science's reach. This is not a failure of science, but a reflection of its nature and scope. Science is a method for investigating the natural world through observation, experiment, and inference. It seeks patterns in nature, formulates hypotheses to explain those patterns, tests predictions derived from hypotheses, and accepts or rejects theories based on how well they match observations. This method has proven extraordinarily powerful. In 400 years, science has transformed our understanding of the universe from pre-Copernican geocentrism to modern cosmology. We have discovered atoms and their constituents. We have revealed the structure of DNA and the mechanisms of evolution. We have detected gravitational waves and imaged black holes. We have traced cosmic history back to 1 second after the Big Bang with confidence and to the Planck time with reasonable speculation. This is an astonishing achievement that would seem like magic to anyone from earlier centuries. But science has inherent limitations that arise from its methodology. It can investigate what exists and how it behaves, but it struggles with questions about why anything exists at all. It can trace causal chains backward in time, but it cannot explain why causation itself exists. It can describe the laws of physics with mathematical precision, but it cannot explain why those laws hold rather than other laws or no laws at all. These are not temporary limitations that better theories or improved experiments will overcome. They are structural limitations built into scientific inquiry. Science investigates the natural world by assuming that nature follows regular patterns describable by mathematics and testable through observation. But these assumptions cannot themselves be justified by science without circular reasoning. We assume nature is lawful in order to discover what those laws are. We assume mathematics describes reality in order to formulate mathematical theories. These are metaphysical commitments that precede and enable science, rather than conclusions science reaches. Karl Popper argued that science progresses through falsification. Scientific theories make predictions that can be tested, and theories that make false predictions are rejected. This distinguishes science from pseudoscience and metaphysics. A genuinely scientific theory must be falsifiable in principle, meaning there must be possible observations that would prove it wrong if those observations occurred. But the question of why anything exists does not yield falsifiable predictions. No possible observation would prove it wrong because the observation itself presupposes existence. Thomas Kuhn emphasized that science operates within paradigms, frameworks of assumptions and methods that define what questions are worth asking and what answers are acceptable. Paradigms shift when anomalies accumulate that the current framework cannot explain. But questions about absolute origins lie outside any scientific paradigm. They cannot be incorporated into normal science because they question the very foundations on which science rests. This does not mean such questions are meaningless or unimportant. It means they belong to philosophy and metaphysics, rather than empirical science. There is a difference between saying science cannot answer this question and saying this question has no answer. The limits of scientific method do not define the limits of rational inquiry or human understanding. Other modes of investigation, other frameworks for seeking truth, may illuminate questions that science cannot address. Nevertheless, science has narrowed the gap between what requires explanation and what does not require or admit explanation. We no longer need to invoke supernatural intervention to explain the sun rising or rain falling or disease spreading. We understand these through natural mechanisms. Similarly, we no longer need to invoke supernatural creation to explain the beginning of the universe. Quantum mechanics provides mechanisms, general relativity provides the framework, inflation provides the driving force. Together they construct a picture of cosmic origins that requires no violation of natural law. The universe's beginning no longer demands miracles in the sense of violations of physical principles. It can be understood as a quantum process, strange and counterintuitive, but entirely within the realm of physics. Whether this counts as creation from nothing depends on how we define nothing. If nothing means the absence of all physical stuff but allows for physical laws and quantum fields, then yes, the universe can arise from this constrained nothing. If nothing means the absence of everything including laws and logic, then no, physics has not explained creation from absolute nothing. But perhaps absolute nothing is an incoherent concept that cannot exist even in principle. Perhaps there must always be something, whether that something is physical stuff or mathematical structure or logical principles. Perhaps being is more fundamental than non-being, existence more natural than absence. This would explain why something exists without requiring a cause for existence. Existence simply is, has always been in some form, and the question of ultimate origin dissolves because there is no ultimate origin, only transformations of what exists. These philosophical speculations cannot be proven or disproven. They remain in the realm of metaphysics, informed by, but not determined by physics. Yet they are the questions that have haunted human consciousness since we first became aware of our existence and wondered why we exist. Modern cosmology has transformed these ancient questions into scientific puzzles about quantum states and field theories, making them more precise and tractable without making them fully answerable. We stand at the precipice of understanding, looking down into the abyss of ultimate questions about existence and non-existence, being and nothingness. We have not reached the bottom. Perhaps there is no bottom to reach. Perhaps the questions recede infinitely like reflections between parallel mirrors. But we have descended far deeper than our ancestors ever dreamed possible. We have transformed the question, how did everything begin from nothing, from mythology to mathematics, from metaphysics to physics, from mystery to mechanisms we can calculate and test. The universe emerged from quantum uncertainty, possibly through tunneling from vacuum state or materialization as described by the Hartle-Hawking wave function. It inflated through exponential expansion, driven by vacuum energy, stretching quantum fluctuations to cosmic scales and creating the seeds of all structure. It cooled and condensed as it expanded, with energy converting to matter through Einstein's equation. Quarks combined into protons and neutrons. Electrons captured by nuclei formed atoms. Gravity pulled matter into clumps that became stars and galaxies. And after billions of years of cosmic evolution, here we are, conscious beings capable of contemplating our origins and asking why we exist. This is not speculation. This is observation combined with theoretical understanding built on experimental physics. The details remain uncertain. The ultimate origin remains mysterious. But the overall picture has solidified into our best understanding of creation. And that understanding reveals something our ancestors could not have guessed. Creation is not past tense, finished, and done. Quantum fluctuations still generate virtual particles throughout space every instant. The quantum vacuum still seethes with activity that never ceases. In eternally inflating regions beyond our cosmic horizon, new pocket universes continuously form, each one a big bang in its own right. Creation is ongoing, perpetual, woven into the fabric of reality itself. We stand at the precipice of understanding, looking down into the abyss of ultimate questions. We have not reached the bottom. Perhaps there is no bottom. But we have descended far deeper than our ancestors ever dreamed possible. We have transformed the question, how did everything begin from nothing? From mythology to mathematics, from metaphysics to physics, from mystery to mechanisms we can calculate and test. The universe emerged from quantum uncertainty, inflated through exponential expansion, cooled and condensed into matter and radiation, evolved over billions of years into the cosmos we inhabit. This is not speculation. This is observation combined with theoretical understanding. The details remain uncertain. The ultimate origin remains mysterious. But the overall picture has solidified into our best understanding of creation. And that understanding reveals something unexpected. Creation is not past tense. Quantum fluctuations still generate virtual particles throughout space. The quantum vacuum still seethes with activity. In eternally inflating regions beyond our cosmic horizon, new pocket universes continuously form. Creation is ongoing, perpetual, woven into the fabric of reality itself. We exist in a universe that creates itself from nothing through quantum processes, that requires no external cause, that may be one of infinite variations in an eternal multiverse. This is stranger and grander than any ancient creation myth. It is a story written in mathematics and confirmed by observation. It is incomplete, uncertain in details, and open to revision. But it is our story, constructed through centuries of observation and thought, the product of our species' long effort to understand its origins. The journey to understand cosmic origins has revealed something unexpected about the nature of physical law itself. The four fundamental forces that seem so different in everyday experience: gravity that holds planets in orbit, electromagnetism that powers our technology, the strong force that binds atomic nuclei, and the weak force that drives radioactive decay, are unified at high energies. This unification is not merely a mathematical convenience or philosophical preference. It is written into the structure of reality, demonstrated through particle accelerator experiments and predicted by symmetry principles. At the Large Hadron Collider near Geneva, protons are accelerated to 99.99999%, the speed of light, and smashed together with energies reaching 13 trillion electron volts. At these energies, particles that normally never interact begin to show unexpected connections. The electromagnetic force and weak nuclear force, which seem unrelated at low energies, merge into a single electro-weak interaction. The distinction between them blurs and disappears. They become different aspects of the same underlying force, related by spontaneous symmetry breaking. This unification was predicted theoretically in the 1960s by Sheldon Glashow, Steven Weinberg, and Abdus Salam, and confirmed experimentally in the 1970s and 80s through the detection of W and Z bosons, the particles that mediate the weak force. The discovery earned all three physicists the Nobel Prize in 1979, one of the great triumphs of 20th century physics. It demonstrated that nature exhibits hidden symmetries revealed only at high energies. Grand unified theories proposed that at even higher energies, around 10 to the power of 16 electron volts, the strong nuclear force joins the electro-weak force. At this scale, quarks and leptons, which seem like entirely different types of particles, become interchangeable. The forces governing their interactions merge into a single grand unified force. This transition occurs at energies far beyond what any conceivable particle accelerator could reach, but indirect evidence supports the idea. The most compelling evidence comes from the running of coupling constants. The strength of each force depends on the energy scale at which you measure it. At low energies, the forces have very different strengths, but as energy increases, these strengths change in calculable ways. The electromagnetic force becomes stronger at higher energies. The strong force becomes weaker. When you plot these curves and extrapolate to high energies, they converge at approximately 10 to the power of 16 electron volts, exactly where grand unification should occur. Moreover, grand unified theories make a striking prediction. Protons, which are stable in ordinary physics, should very slowly decay into lighter particles. The predicted lifetime is enormous, about 10 to the power of 34 years, far longer than the age of the universe. But with enough protons, you might observe a few decays. Experiments have been built deep underground, shielded from cosmic rays, containing tens of thousands of tons of ultra-pure water, surrounded by detectors looking for the flash of light from proton decay. So far, no confirmed decays have been seen, setting limits on the proton lifetime that challenge the simplest grand unified theories, but don't rule out all versions. At the Planck energy, approximately 10 to the power of 19 electron volts, even gravity enters the unified picture. At this scale, quantum effects in space-time itself become important. The smooth geometry Einstein described fragments into quantum foam. All four forces merge into a single superforce governed by a still unknown theory of quantum gravity. This is the regime where string theory and loop quantum gravity operate, attempting to describe reality at the most fundamental level. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, loops of energy, whose different vibration modes correspond to different particles. An electron is a string vibrating one way. A quark is the same string vibrating differently. A photon is another vibration mode. All particles are unified as different notes played on the cosmic string. This elegant idea automatically includes gravity, solving the problem of unifying quantum mechanics with general relativity. The graviton, the hypothetical particle that carries gravitational force, emerges naturally as a particular vibration mode. But string theory requires 9 spatial dimensions rather than the 3 we observe. Where are the extra 6 dimensions? They must be compactified, curled up so small we cannot detect them. Imagine a garden hose viewed from far away. It looks like a one-dimensional line. Up close you see it has thickness, a second dimension curled into a circle. Similarly, what we perceive as a point in 3-dimensional space might actually be a tiny 6-dimensional shape curled up at the Planck scale. The shape of this compactification determines the physics of the 3-dimensional world we observe. Different shapes yield different particle masses, different force strengths, different cosmological constants. This is the string landscape, the vast space of possibilities arising from different compactification geometries. Estimates suggest approximately 10 to the power of 500 different possible vacua, each corresponding to a different 3-dimensional physics. Our universe occupies one point in this landscape. Other points might be realized in other pocket universes in the eternal multiverse. Loop quantum gravity takes a different approach. Instead of adding extra dimensions, it quantizes space-time itself. Space is not continuous but discrete, woven from loops of quantum geometry connected in a network. At scales larger than the Planck length, this network appears as smooth continuous space, just as a fabric appears smooth until you examine it closely enough to see individual threads. The theory eliminates singularities by replacing them with bounces or transitions. The Big Bang singularity becomes a big bounce, from a contracting phase to an expanding phase. Other approaches to quantum gravity exist as well. Causal set theory proposes that space-time is fundamentally discrete, composed of point-like events connected by causal relations. Asymptotic safety suggests gravity might be quantum mechanically consistent without requiring new physics at the Planck scale if coupling constants flow to particular fixed points at high energy. Emergent gravity proposals argue that space-time and gravity are not fundamental, but arise from more basic quantum degrees of freedom, perhaps quantum entanglement. Despite decades of effort from thousands of physicists, we do not yet have a confirmed theory of quantum gravity. No experiment has tested these ideas directly. No observation has definitively ruled out alternatives or confirmed one approach. We remain in the frustrating position of having multiple theoretical frameworks that are mathematically consistent and conceptually appealing but empirically unverified. This is partly because the Planck scale is so far beyond current experimental reach. The Large Hadron Collider probes energies 10 to the power of 4 electron volts. The Planck energy is 10 to the power of 19 electron volts, 15 orders of magnitude higher. Building an accelerator to reach Planck energies would require a ring larger than the solar system. Yet quantum gravity is not mere speculation disconnected from observation. It is the theory that must describe the Planck epoch, the first instance of cosmic history. It determines what happened at the Big Bang. It explains whether the singularity is real or an artifact of classical gravity. It predicts the initial conditions that led to inflation. Understanding cosmic origins requires quantum gravity, even if we cannot test it in particle accelerators. Some physicists hope that cosmological observations will provide indirect tests. The pattern of fluctuations in the cosmic microwave background might preserve signatures of quantum gravity effects from the early universe. The polarization of this radiation might reveal gravitational waves produced during inflation, testing predictions about the inflaton field and its quantum fluctuations. The distribution of galaxies on the larger scales might show subtle deviations from predictions based on classical gravity, hinting at quantum corrections. These are long shots. The effects are expected to be tiny, easily lost in observational noise, but cosmology offers our best hope for testing quantum gravity because the early universe is the only place where quantum gravity effects were large enough to leave observable consequences. In this sense, the universe itself is the only laboratory we will ever have for testing our most fundamental theories about the nature of space, time, and gravity. The quest for a final theory, a single unified framework that explains all forces and all particles from first principles, drives much of theoretical physics. Einstein spent the last 30 years of his life searching for such a theory and failed. We have made progress since then, unifying electromagnetism with the weak force, understanding how the strong force works, developing candidates for quantum gravity. But the final theory remains elusive. Perhaps it is string theory, waiting for us to understand it better and make testable predictions. Perhaps it is loop quantum gravity once we solve its open problems. Perhaps it is something completely different that no one has yet imagined. Or perhaps there is no final theory. Perhaps the tower of explanations extends infinitely downward, each theory explaining the previous, but requiring a deeper theory beneath it. Perhaps reality is irreducibly complex, admitting multiple complementary descriptions but no single ultimate description. Perhaps the question of why these laws rather than others will always remain beyond physics, forever in the domain of metaphysics. The answer matters profoundly for understanding cosmic origins. If there is a final theory, it should explain itself, requiring no input except perhaps pure mathematics and logic. It would generate the laws of physics from first principles, making our universe inevitable rather than contingent. If there is no final theory, then the laws of physics are contingent facts about our universe, true here but possibly different elsewhere in a multiverse, and the question of why these laws becomes less urgent because all possible laws are realized somewhere. We stand at an extraordinary moment in human intellectual history, closer to understanding ultimate origins than ever before, but still frustratingly far from final answers. We have theories that work magnificently within their domains. We have observations that confirm those theories to astonishing precision. We have mathematical frameworks that unify disparate phenomena and reveal hidden connections. But we do not yet have a complete, consistent, experimentally verified theory that explains how everything began from nothing, why anything exists, or what the universe ultimately is. The next decades will bring new observations that test our understanding of cosmic origins with unprecedented precision. The James Webb Space Telescope, launched in December 2021, is observing the most distant galaxies ever seen, pushing back to within a few hundred million years of the Big Bang. These observations will reveal how the first stars and galaxies formed, testing our understanding of structure formation in the early universe. Ground-based observatories like the Vera Rubin Observatory in Chile will survey the sky repeatedly, cataloguing billions of galaxies and measuring their properties with extraordinary accuracy. This will map the large-scale structure of the universe in 3 dimensions, revealing the distribution of matter and dark matter, testing predictions about inflation and the growth of cosmic structure, and perhaps finding signatures of new physics in the pattern of galaxy clustering. Gravitational wave detectors offer a completely new window on the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, has already detected dozens of black hole mergers and neutron star collisions. Future detectors will be even more sensitive, possibly detecting gravitational waves from the inflationary epoch itself. These primordial gravitational waves, if they exist, would be the smoking gun confirming inflation happened and testing specific inflationary models. The cosmic microwave background will be measured with even greater precision by future missions. The Simons Observatory and CMB S4 experiments will push sensitivity to the limits of what is possible from the ground. A future space mission might detect the polarization signature of primordial gravitational waves or measure temperature fluctuations with such accuracy that tiny corrections from quantum gravity become visible. Each improvement in measurement constrains theoretical possibilities and might reveal unexpected phenomena. Particle physics experiments at the LHC and future accelerators will continue probing the fundamental forces in particles. The discovery of the Higgs boson in 2012 confirmed the mechanism of electroweak symmetry breaking, but mysteries remain. Is the Higgs fundamental or composite? Are there additional Higgs bosons? What is dark matter? Why do neutrinos have mass? Each answer constrains our understanding of particle physics at high energies, and thus the conditions in the early universe. The convergence of these observations from cosmology, gravitational waves, particle physics, and quantum gravity might finally reveal the physics of the Planck epoch. We might discover signatures of string theory in the polarization of the cosmic microwave background. We might find evidence for loop quantum gravity in gravitational wave signals. We might detect proton decay and confirm grand unification. Or we might find something completely unexpected that forces us to revise our theories entirely. This is how science progresses, through the interplay of theory and observation, prediction and confirmation, speculation and experiment. Each generation inherits the understanding developed by previous generations and builds upon it, pushing slightly further into the unknown, revealing slightly more of the hidden structure of reality. The questions we ask become more sophisticated, the answers become more precise, but new questions always emerge, deeper and more challenging than those we answered. The ultimate question of why there is something rather than nothing may never be fully answered by science. It may lie permanently beyond empirical investigation in the realm of metaphysics and philosophy. But even if we cannot answer why, we can answer how with increasing precision and confidence. We can trace the chain of causation backward to the Planck epoch. We can describe the quantum state of the universe at its beginning. We can explain how space-time and matter and energy emerge from that state through processes governed by physical law. This is an extraordinary achievement that would have seemed impossible to scientists even a century ago. In 1924, we did not know that other galaxies existed beyond the Milky Way. We did not know the universe was expanding. We did not know about quantum mechanics, or nuclear physics, or the structure of atoms. In 90 years, we have progressed from near total ignorance about the cosmos to a detailed understanding of 13.8 billion years of cosmic history. We know what the universe was like when it was 1 second old. We can calculate conditions when it was 1/billionth of a second old. We can speculate responsibly about 10 to the power of negative 43 seconds after the beginning. This progress shows no sign of stopping. Each generation of telescopes reveals fainter, more distant objects. Each generation of detectors measures phenomena with greater precision. Each generation of theorists develops more sophisticated mathematical frameworks. The future holds promise of answers to questions we can now barely formulate and discoveries we cannot yet imagine. The question that began this journey remains profound. and perhaps ultimately unanswerable within science. Why is there something rather than nothing? We cannot answer this completely. Physics cannot step outside the universe to view it from the perspective of absolute nothingness. But we have learned that quantum mechanics make something more natural than nothing, that the laws of physics permit creation without external causes, that the universe can be self-contained and self-explanatory within the framework of natural law. This is not a final answer. It is an extraordinary achievement of human understanding that transforms ancient questions into modern science. The boundary between known and unknown has shifted dramatically. What was once complete mystery has become detailed physics. What was once miracle and magic has become mechanism and mathematics. The transformation is incomplete and perhaps will always remain incomplete, but it represents genuine progress toward understanding the deepest questions about existence. The question that began this journey remains profound. Why is there something rather than nothing? We cannot answer this completely, but we have learned that quantum mechanics make something more natural than nothing, that the laws of physics permit creation without external causes, that the universe can be self-contained and self-explanatory within the framework of natural law. This is not a final answer. It is an extraordinary achievement of human understanding that transforms ancient questions into modern science. The question that began this journey remains profound. Why is there something rather than nothing? We cannot answer this completely, but we have learned that quantum mechanics make something more natural than nothing, that the laws of physics permit creation without external causes, that the universe can be self-contained and self-explanatory within the framework of natural law. This is not a final answer. It is an extraordinary achievement of human understanding that transforms ancient questions into modern science. We have discovered that the question itself may be misconceived. The sharp distinction between something and nothing blurs at the quantum level. The vacuum is not empty. Fields fluctuate. Virtual particles appear and vanish. Space and time themselves may be emergent from deeper quantum structures. What we call nothing may be impossible. The lowest energy state of quantum fields still contains activity. Perfect stillness is forbidden by the uncertainty principle. We have learned that creation is not a one-time event in the distant past. If eternal inflation is correct, creation continues throughout the multiverse. New pocket universes nucleate constantly from the inflating background. The process is ongoing, eternal, woven into the fabric of reality. We are not looking back at a singular moment of creation, but inhabiting an evergreen cosmos that perpetually creates itself. We have discovered that our universe may be one of countless others, each with different properties, different laws, different histories. The multiverse hypothesis is controversial, perhaps untestable, certainly strange. But it emerges from our best theories rather than being added by hand. Inflation naturally becomes eternal. String theory naturally predicts a landscape. We did not choose these features to solve philosophical problems. They arose from mathematics developed to explain other phenomena. We have found that the deepest questions about existence may lie beyond science's reach. Why do the laws of physics exist? Why does mathematics describe reality? Why is there logical structure rather than chaos or nothingness? These questions may have no answer within physics, because physics itself requires them as foundations. We may need to accept some level of brute fact, some ultimate explanation that requires no further explanation. Yet what we have achieved is remarkable. We have pushed the boundary of understanding back to within one Planck time of the beginning. We have proposed mechanisms by which universes can emerge from quantum states without violating physical law. We have developed mathematical frameworks that describe creation, even if we cannot yet fully solve those equations. We have transformed mystery into mechanics, revelation into research programs. The journey from ancient creation myths to modern cosmology represents one of humanity's greatest intellectual achievements. Our ancestors looked at the night sky and imagined gods and monsters. We look at the same sky and see quantum fields, curved space-time, and the afterglow of creation. Both perspectives sought to understand our origins, but we have tools our ancestors lacked. Telescopes that see across the universe, accelerators that recreate conditions from the first moments, mathematics that lets us calculate what we cannot directly observe. This knowledge comes with humility. The more we learn, the more we realize how much remains unknown. Dark matter constitutes most of the universe's mass. yet we do not know what it is. Dark energy drives cosmic acceleration, yet we do not understand its nature. The quantum gravity theory needed to fully describe the Planck epoch remains incomplete. The multiverse, if it exists, may forever lie beyond direct observation. But science progresses through iteration. Each generation builds on the work of those before. Einstein built on Newton. Quantum mechanics emerged from classical physics. Inflation extended the Big Bang. String theory attempts to unify quantum mechanics and gravity. The Wheeler-DeWitt equation tries to describe the quantum state of everything. Each step reveals new mysteries even as it solves old ones. We live in an extraordinary time. For the first time in human history, we can seriously investigate the origin of everything using scientific methods. We have evidence from the cosmic microwave background. We have theoretical frameworks from quantum field theory and general relativity. We have computational tools to run simulations. We have satellites mapping the sky with incredible precision. The question of cosmic origins has moved from mythology to mathematics. What would ancient philosophers make of our discoveries? Parmenides argued that nothing cannot exist, therefore the universe must be eternal. He was wrong about eternity, but perhaps right about nothing. Quantum mechanics shows that perfect nothingness is unstable, impossible, forbidden by the uncertainty principle. Something truly is more natural than nothing, though not for the reasons Parmenides imagined. Aristotle argued against creation from nothing as violating logic. Yet quantum mechanics permits exactly this through vacuum fluctuations and quantum tunneling. The universe can borrow energy for brief moments. It can tunnel through classically forbidden barriers. It can exist in superpositions of different states. Aristotle's logic was classical. The universe is quantum. The medieval philosophers debated whether the world had a temporal beginning or had existed eternally. Thomas Aquinas argued that reason alone could not decide the question, which required divine revelation. Modern cosmology shows he was half right. The observable universe had a beginning, but whether physical reality itself had a beginning remains uncertain. The multiverse may be eternal even if our pocket universe is not. The existentialists wrestled with the absurdity of existence itself. Why is there something? Heidegger made this the fundamental question of metaphysics. We have not fully answered it, but we have transformed it. The question now involves specific physical mechanisms, testable predictions, mathematical frameworks. It remains profound, but it is no longer purely philosophical. If you found this exploration of cosmic origins fascinating, hit that like button and subscribe for more deep dives into the mysteries of the universe. We have barely scratched the surface of modern cosmology. Future episodes will explore dark matter, dark energy, black holes, and the ultimate fate of reality itself. The universe reveals its secrets slowly, but each discovery makes the cosmos more wondrous and more strange. The question of how everything began from nothing may never receive a complete answer, but we have come astonishingly far. We understand how quantum fluctuations become cosmic structure. We understand how inflation solves cosmological puzzles. We understand how vacuum energy drives exponential expansion. We understand how the laws of physics permit creation without external causes. These are not mere speculations, but predictions tested against observation. The cosmic microwave background confirms inflation's predictions. Galaxy distributions match simulations based on quantum fluctuations. The universe's flatness agrees with theoretical calculations. Our understanding is incomplete, but it is grounded in evidence and constrained by experiment. We exist in a universe that emerged from quantum uncertainty, inflated through exponential expansion, cooled and condensed into matter and radiation, evolved over billions of years into stars and galaxies and planets and life. This story is written in mathematics and confirmed by observation. It is strange, beautiful, and profoundly alien to common sense. And perhaps most remarkable of all, we are the universe's way of understanding itself. The atoms in your body were forged in stellar furnaces. The calcium in your bones, the iron in your blood, the carbon in your cells, all created through nuclear fusion in stars that lived and died before the sun was born. We are made of star stuff, as Carl Sagan memorably said. But more than that, we are the universe contemplating its origins. 13.8 billion years after creation, complex arrangements of matter and energy have become conscious. They wonder where they came from. They build telescopes and accelerators. They develop quantum mechanics and general relativity. They peer back toward the beginning and ask, how did everything begin from nothing? We may never have a final answer, but the asking, the investigating, the discovering, this is what makes us human. We are the universe awakening to itself, tracing its history backward through time, approaching the ultimate mystery of existence. And in that quest for understanding, we find meaning and wonder beyond measure. Thank you for joining me on this journey to the beginning of everything. Until next time, keep looking up and keep questioning. The universe is stranger and more magnificent than we can imagine, but through science we can at least begin to understand it.